Can we remove that one? So we, right. Okay, welcome everyone. Thank you so much for joining us today for the Grasp on Robotics talk series. I am Nadia Figueroa. I am the Grasp faculty host for today's talk. And a quick reminder, previously recorded talks can be found on our Grasp YouTube channel and website. If you are joining us via Zoom, please submit your questions using the Q&A button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. If you are here in person in Wenchen, you will have an opportunity at the end of the talk to provide your questions to the panelists. Please be sure to use a handheld mic when speaking so our online audience will be able to hear you, and also Julie, hear your questions as well. Our panelists are Tianyu Li, who's a PG student in my group, and Yifei Simon Chow, who's a PG student advised by Pratik, VJ, and also collaborating with me. So it is my pleasure to introduce Julie, who is the H.N. Slater Professor of Aeronautics and Astronautics. She is the faculty director of MIT's Industrial Performance Center and director of the Interactive Robotics Group, which aims to imagine the future of work by designing collaborative robot teammates that enhance human capability. She is expanding the use of human cognitive models for AI and has translated her work to manufacturing assembly lines, healthcare applications, transportation, and defense. Before joining the faculty at MIT, she worked at Boeing Research and Technology on robotics applications for aerospace manufacturing. Julie has many, many awards. She has been recognized by the NSF Foundation with the Faculty Early Career Award, the MIT Technology Review on its 35 Innovators Under 35 list. She was also the recipient of the 2018 IEEE RAS Academic Early Career Award for her pioneering contributions to human-robot collaboration and transition of results to real-world applications. She has received international recognition in form of paper awards, nominations for HRI, American Institute of Aeronautics and Astronautics, Human Factors and Ergonomic Society, the International Conference on Automated Planning and Scheduling, and the International Symposium on Robotics. She earned her degree in Aeronautics and Astronautics in Autonomous Systems from MIT, and is the co-author of the book, What to Expect When You're Expecting Robots, The Future of Human-Robot Collaboration. And she was actually the reason that I'm here today. So she was my postdoc advisor. And she really helped me a lot during my postdoc and faculty search. So Julie, welcome to Penn, and take it away.
Hi, Nadia. Thank you so much. I'm delighted to be able to talk with you today and share with you a bit about the recent research from our lab. So thank you for the very, very comprehensive introduction, Nadia. So a little bit about the technical work that my lab does, and then a little bit about the other roles that I have at MIT. I lead the Interactive Robotics Group as a part of CSAIL, and as a part of that work, we aim to develop intelligent machines, intelligent robots that are capable of collaborating with people more effectively, the way people are able to collaborate with other people in a variety of settings, including high-stakes settings. And for the past about 5 years or so now, I've also had the wonderful opportunity to collaborate across disciplines at MIT with social scientists and others on topics related to future of work. And now lead cross-disciplinary teams looking at how increased uses of automation and AI can go hand in hand with better quality jobs. And so today I'll talk a little bit about the recent work from our lab and thinking about how we can architect more effective human-machine partnerships in the increasingly high-stakes settings in which AI and robots are being deployed. And this work stems from research that we conducted as a part of these cross-disciplinary teams, as a part of MIT's task force on the work of the future, which ran 2018 to about 2021. And as a part of that research effort, students from my lab, engineers, collaborated with social scientists and conducted site visits and interviews around the world, looking at the introduction of new technologies, in particular in manufacturing, Industry 4.0 technologies, looking at how they were being utilized, coming on a decade after the sort of push for Industry 4.0. What was working, what wasn't meeting expectations, and what could we expect going forward. Similarly, I had students travel to and embed out at NASA, looking at tactical planning for the Mars rover, and looking at the technologies that they were bringing in support of that very complex sort of planning endeavor. And as my students so eloquently described when they came back, this is what they expected to see: robots everywhere, automation in sort of decision support as a part of these complex mission planning processes. And all of that is prefaced with, our lab has spent years developing technology and, feeling that we're relatively successful in being able to translate and see impact for that work with industry partners and others. And they came back and said, this is a disaster. Nothing we're developing in the lab or anyone else's is actually being used. And why is that? And they went to the other faculty on the task force, which I thought was really funny, and told them, like, we're very upset because we're suddenly realizing that, everything that we're doing in the lab isn't useful. And my dear faculty colleagues kindly told the grad students in my lab, what do you mean? Like, your lab is one of the only, one of the labs that really pushes towards making technologies that can be useful. And so there was this disconnect, but from that disconnect comes the best research and the best ideas for how we do the most impactful work. And from those site visits and interviews, the team came back with quotes and more rigorous study of the reasons that these technologies aren't adopted and aren't used at scale. So we heard they're too opaque and unpredictable. We can't trust them to perform safety critical or value-adding tasks. They're too inflexible, single purpose. They're too difficult to program, especially for those that aren't programming experts. Well, much of our work had focused on enabling robots that were not just safe enough to work alongside people, but also smart enough to work flexibly with people. These challenges sort of, point to the really importance of sort of other research emphases, looking at transparency of AI systems, explainability, ease of use, accessibility of robot programming. And much of our lab's efforts in the past 5 years or so have focused on aiming to better understand and address these challenges. So, while on the manufacturing side, we see very little use of an adoption of advanced automation. In fact, just to underscore that point, even just 1 in 10 manufacturers in the US, and that includes like the big automotive manufacturers that do use robots, only 1 in 10 from small to large have a single robot. And most are low users of that single robot. So, you really do see, this lagging adoption of these technologies. And it's not for lack of need. So, in manufacturing, there are somewhere around 700,000 job openings currently. So there's a labor crisis and really a desire to be able to use these technologies. But we don't see them, being successful in addressing those challenges. And on the flip side, there are other sectors that are just leaping ahead and sort of leading the frontier in this. Healthcare, has moved forward to incorporate a lot of advanced technology, and we learn from the challenges that they've been facing in doing that. And on the DoD side, some very innovative programs in human autonomy teaming, in which fighter pilots are flying their own ship, but are also supervising autonomous and semi-autonomous aircraft as a part of missions. And what's I think what's really interesting here is when you look at these new programs in the Air Force in collaborative autonomy, there's a directive and a requirement to incorporate more advanced capability in a way that, quote unquote, ensures appropriate levels of human judgment. And obviously, this is imperative for healthcare as well. And so the question is, what does it mean to ensure appropriate levels of human judgment? And that's the topic that I want to sort of talk through today together in this talk. So now we have like two diametrically opposed ends of this spectrum. We have, say, manufacturing as an example that is like vastly lagging in adoption of and utilization of these systems with dire need. We have these other sectors that are really pushing forward and are incorporating the most advanced technologies in very complex settings. But fundamentally, the challenges they're facing are very, very similar with regard to flexibility, with regard to transparency, with regard to trust. And the last point I want to make is that while these are two ends of the spectrum, we can expect to face similar challenges in the increasing utilization of AI, across other sectors of the economy as well. So this is a challenge beyond manufacturing, healthcare, and aerospace. And one of the pointers to that is, again, the current labor crisis and shortage across many sectors, the changing demographics of our country. Even immigration policy is playing into this. And there's increased urgency and need to be able to incorporate new technologies to improve productivity. The emphasis is less on concern about supplanting human labor or opportunity, but more on being able to fill the gap, from the limitations of the labor market. So with that increased pressure, we need to ask, how do we incorporate this technology in a way that, first of all, supports appropriate human judgment and oversight of it, but then also leads to higher quality rather than lower quality jobs. And so, the challenges that we face in incorporating more advanced technology, thinking specifically about AI, deep, highly parameterized AI models, including generative AI, the challenges we face in doing that are well documented, even in the introduction of more traditional forms of automation. So we know from human systems and human factors that very extensive study that increased automation results in very serious negative consequences. This can manifest as an operator failing to identify a problem as it occurs, undermining their ability to appropriately intervene. Issues related to overtrust in automation or complacency, just sort of hitting go when the system is not producing appropriate outputs. Loss of situational awareness, and I'll spend some time talking about this. And then degradation of skill, the ability to actually perform the work yourself, which we saw back from aviation as sort of direct or manual control tasks, but we can see in many other settings for skilled work as we introduce automation. You could see it in your car, just navigating around using GPS. So with these concerns, circa 2016, we saw significant investment in explainable AI. There's no, widely accepted definition for AI transparency, but in supporting AI transparency, definitions usually, incorporate the need for understanding and predictability of the AI decision-making system, and enabling a user's comprehension about its intent, performance, future plans, and reasoning process. And so, the push for XAI was to develop systems that can support this by explaining their rationale, characterizing their strengths and weaknesses, and conveying an understanding of how they'll behave in the future. But what's kind of lacking from this is the details of how exactly the XAI system does this and how you evaluate whether it's doing this well and sufficiently to avoid the negative consequences of increased use of automation. And we also have this sort of criticism, self-criticism in the field, that many of the explainability techniques that we develop, they're really made for AI experts and designers. They're not really made for the end users that we talk about and sort of worry about in the context of these new applications. And so there's been a push in recent years from a number of research and applied research and industrial institutions to look at how we can bring a human factors approach to explainable AI, to bring what we know about the rigorous methodologies and principles we have for design of human automated systems to enhance human machine performance. And so this is sort of the lens with which our lab also approaches the research that we're doing. And I'll talk a little bit about this research in terms of how XAI can support a person, so more holistically, not just in task performance, but in these other human factors constructs that we know are so important: situational awareness, workload, and trust. And then how we know if we're succeeding, and how do we bring all of this to be able to evaluate a little more critically explainable AI and the role it's serving and the purpose that it's serving, in terms of like what should explanations explain and what should we expect to see from that. So I want to dive a little deeper into situational awareness, because this is really core. It's something different than performance. So situational awareness, the study of situational awareness, sort of emerged with the increased introduction of automation in aviation, but in other sectors as well. And it's widely recognized as very important to design of systems in sort of high stakes environments. So situational awareness is defined as the ability of a person to perceive, comprehend, and project the state of an environment. So that's important for driving. It's important for surgeons and surgical techs in an operating room. It's important for bomb disposal technicians. Many sectors, and in particular, loss of situation awareness while operating highly autonomous systems is identified via the NTSB as the cause of many deaths in commercial and general aviation. So it's a lot of study has gone into this. And it's understood that humans must maintain situational awareness, not to perform their job in nominal or sort of regular circumstances, but in order to be able to handle the unexpected when things, go off plan, to be able to effectively take control of a job in the event, for example, of a machine failure. So, situational awareness is defined as a construct with 3 levels. The first level is regard to like what we perceive in our environment in a volume of space and time. The second level is how we take those elements and make meaning of them. And the third is how we project their status into the future. And just in the context of aviation, you can think about level 1 perception as, within your aircraft, like what is your fuel level? What are the elements that matter towards performing your task of flying this aircraft? Fuel level, one of them. And you would comprehend your fuel level in terms of what it means for the range of your aircraft. And then you would project, is your destination reachable or not? So building on this framework, we know we have to be able to maintain situational awareness of our environment, of other people in the environment, of the task itself, and the sort of procedural elements of how we perform a task. But as we introduce increasing automation, enabling a person to maintain situational awareness of that automated technology or AI technology is another critically important part to this that requires a very careful attention. And so superstar recent PhD from my lab, Lindsay Sandeman, brought this sort of situation awareness framework from human factors and sort of framed it in the context of what it means for explainable AI, and developed the situational awareness framework for explainable AI, safe AI framework. And this has been taken up and received significant interest from large programs within the Air Force, from the FAA, in other settings. And so the goal here is to be able to enumerate the requirements and information needs for XAI at these 3 levels. So level 1, perception. This is what we need to understand about the features of our AI itself in terms of its inputs and outputs. Comprehension is regarding the model details. It's answering why and how questions for how the system, your automated system or AI system, is operating. And then level 3 relates to projection, what if type questions. So looking at alternate inputs, alternate outputs, to be able to explain what would happen in the future under different scenarios, or predictive capability of that system projected out. So the safe AI framework, much like SA, in other contexts, is valuable for enumerating informational needs, We'll talk about how it's applicable for identifying the techniques you can use, the XAI techniques you can use to explain your system. And then it has been used for identifying capability gaps and future needs, and evaluating explanation quality. So I'm sort of giving you a priming here, and then I'm going to talk about some of the recent work from the lab and how it fits within this framework. So SA is not the only human factors construct that's critically important for us to design for and to be able to assess, but there's interaction effects with workload as well. And so workload relates to like the mental resources that's demanded of a task, and that's can be supplied by a human. So the task requires some cognitive resources from us. We have some cognitive resources to give. Is it more? Is it less? What do we have left over for other tasks? And there's very rigorous models with physiological foundations regarding cognitive workload. So it turns out like there's different parts of our brain and processing mechanisms for types of input: visual, auditory, haptic. There's stages of processing of these types of inputs, and then the workload associated with how we respond to them. All utilize different sort of buckets of resources cognitively. And so it's a very, very interesting model, and it has implications for how you assess workload and also how you design for workload. So you can share a little bit better, across modalities than within modalities. When we talk about explainable AI, the local workload, the sort of processing load that we have for dealing with a single explanation is important, as is the sort of global workload. As we're interacting with this system in a high stakes, high time pressure environment, the workload associated with interaction with the new automated or AI system is very important to characterize as well. And then finally, we have trust. So, trust is defined as an attitude that an agent, AI, or person will help achieve an individual's goals in a situation characterized by uncertainty and vulnerability. And our goal here is not to just engender blind trust, but to be able to support trust calibration. The goal here is to be able to support a person in identifying when they should rely or comply with an automated system, or take over and perform or compute themselves rather than rely on the system. So there's very interesting interaction effects among these three constructs. So when we think about how we enable appropriate judgment or oversight of these systems, we do need to be able to think about not just how the system performs a task, its performance level, but how it supports a person's situational awareness, how it affects cognitive workload, and supports ability to calibrate effective trust in the system. So now what I want to do is talk about XAI in the context of Ensley's 3-level situation awareness model, and kind of look critically as to how well we're able to achieve or support a human's essay on these 3 levels with existing techniques. So I'll start with level 1 essay, our ability to perceive relevant elements and attributes in the environment. And I want to make you feel as though, which is, I think, supported empirically, that we have a very shaky foundation when we're using existing explainability techniques and supporting level 1 essay. So widely used explainability technique that relates to level 1 essay are feature attribution techniques or saliency map techniques, which are local computations that are conveying the contribution of individual features as a part of, say, a classification decision. So here in a mortgage application, what is the individual contribution of each of these features to the final decision of a mortgage application being denied? Similarly, saliency map techniques are computing locally within pixels about the relative contribution of pixels to the classification technique. And you can see different techniques highlight sort of different pixels, but with many of these, you get a sense that this image is identified as a bird because those pixels are highlighted. And similarly for sentiment analysis, highlighting the contribution of individual words. And the concept here is via these attribution techniques is that changing values of more important features should have a larger impact on the model prediction. And so, we naturally, as I'm sure all of us do, understand that we take these features that this explainability technique is providing us, and we're making sense out of them. So if we look here, looking at this wolf, if this husky is classified as a wolf, we can see that the explainability technique is highlighting pixels related to the snow in the background. That tells us maybe we need to augment our data set and show more pictures of wolves without snow. Helps us maybe identify spurious background correlations. It also helps us build an understanding of how a model is operating, including the biases that are kind of reinscribed through training on human source data. So in this case, you can see the saliency technique is highlighting emergency room and her. And you can see the mask prediction is the nurse rushed to the emergency room to see her patient. And we can infer from that there is kind of some gender bias potentially in the model here. So we build our cognitive understandings from these local explanations. And they're used in high stakes settings as well. So in identification or classification of tumors in medical images, saliency techniques are highlight regions that are sort of suspicious that may contribute to the classification of there being a cancerous lesion in the image. So the question that PhD students Yalun and Serena from my lab had was, well, are these explanations sort of necessarily correct? So the question here is, these are local explanation techniques that are approximating an extremely high dimensional space. So how well do they perform in the context of, if we know a feature is crucial to a model prediction, can these feature attribution techniques identify its importance? And to be able to answer this question, Yalun developed this data modification assessment approach, where the idea was we want to be able to construct a data set where we definitively know the only pixels that are used in the classification of that image. And then we want to identify whether these saliency methods or feature attribution methods are identifying those pixels that can be the only ones that are contributing to the classification. So the way to do that is to take images with labels like crow, sparrow, and modify those labels, based on a random coin flip, so that nothing in the actual image itself can be used to predict the label associated with them, and then include modifications on that image that do correlate with the label. So these watermarks, for example, or other labels. We use blurring, other modification techniques as well. But essentially, the modification technique is the only element that is predictive of the label. And then you train a high-performing classifier, and they do tend to be very high-performing. So we know the classifier must be using these sort of modified elements of the image, and then you apply them in various places on the image. This is an example of, some of these modification techniques are very subtle, not just watermarks, but very subtle sort of blurring at the edges or in the center of the image. And then ultimately applying a feature attribute method to be able to identify, what is the sort of percent of pixels captured by the explainability technique as compared to what we know to be the ground truth pixels contributing to the prediction or the classification. So how would you guess that many of our most popular and widely used explainability techniques work with regard to this? Unfortunately, I'm not there in person and I can't see the chat. But the very fact that I labeled it a shaky foundation should tell you not all is not good. So here, we're showing applying Shah with sort of the watermark, sort of a very salient modification. Here, the green, so looking at the percent attribution inside the injection region of that watermark. Green is good. Red is essentially random chance. X-axis is the region size for the feature that was injected. And you can see, well, it's kind of towards the green, not really hugging the green line, but in the right quadrant, sort of. So seems to be working okay, but obviously, not perfectly. And then you look at other saliency techniques with a variety of modifications, and you see actually some of these don't perform very well at all. So, not all methods are performing equally well in identifying the truly important features, and some are really, arguably not much better than kind of random chance here, which is not good, because these are the techniques that we're using to build our level 1 essay for how these systems work. And the practical implications of this are very significant. So some of you may remember sort of the news articles from a while ago of an extremely high-performing classifier of cancer and mammograms. But it turned out that the primary feature that was being used, the spurious correlation, was like a label injected by a particular lab. And it just so happened that lab was referred the sort of most probable cancer patients. So, maybe they were able to image faster, or they were the preferred, imaging location for that facility. But obviously, like bias, selection bias, and who was provided to that facility, coupled with the use of a watermark, a very unique marking on their scans, is what ultimately resulted in that high performance. And a saliency technique, what we show empirically, may very well not expose to you that is the spurious correlation that's actually being used in the prediction. So, so some explainers don't work for known spurious correlations, and that can have wide-reaching implications for use of these techniques in many of these high-stakes environments. Okay, so that's level 1 essay. Next, let's talk about level 2 essay. And this is about comprehension. I think we shouldn't get into an argument as to whether machines comprehend or not. I don't think machines really comprehend, but humans do comprehend. So how is XAI supporting a human's ability to comprehend? As we see, we are performing comprehension based on the features that were provided from these explainability techniques. And that raises a number of questions. So can humans comprehend the behavior of their autonomous or AI system? And you can ask a number of questions related to that umbrella. But one of the questions is, well, how good are humans at writing reward functions, specifying for a system what they intend for it to do? And how well does an explainability technique support a person's understanding of the reward function or objective of that agent? So going in the first direction, how good are people at specifying reward functions? I mean, we know regarding the alignment problem that people are generally not very good at it. Reward functions are often wrong or underspecified. And we have these sort of loophole examples of how systems play a game in ways that you wouldn't expect because it's the way that they can accrue more points. And so, related to this topic, a PhD student, Serena Booth, recent PhD from my lab, Serena Booth, had some questions around sort of the process by which AI researchers, RL experts, specify rewards. So we know that there's many of us use sort of a trial and error process to develop rewards, and are undergoing, as a part of that process, sort of an unsafe shaping process of that reward. And she was interested in looking at what the implications were of that sort of trial and error reward design, and looked at this in the context of the hungry-thirsty domain, which has been studied in the past, a relatively simple domain where an agent it needs to eat. The goal is for the agent to eat as much as possible, but the agent can only eat if it's not thirsty. And if the agent drinks, it becomes not thirsty. If the agent doesn't drink, it becomes thirsty with 10%. And we know that sort of the sparse, unshaped reward function for this is pretty simple. Like if you're not hungry, not thirsty, that's 1. If you're not hungry and thirsty, that's fine because you're not hungry. If you're hungry and not thirsty, that's actually not good because you're hungry. And if you're hungry and thirsty, that's not good either. So this is sort of the true ground truth sparse reward function, which we can at least agree upon for this simple domain. And the true performance measure is ultimately the number of time steps in which the agent is not hungry. So all simple enough. Now, interestingly, in Serena's study, she conducted a controlled observational user study with RL experts and investigated this phenomena in which she was able to confirm actually, study participants overfit as they're sort of through trial and error defining reward functions. They're overfitting that reward function. They're shaping it in an unsafe way and then actually overfitting it to the particular algorithm choice and the particular parameters. So that's not ideal. But what I want to highlight here is another observation from her study. So she had these 30 participants basically specify the reward with weights to these states, and then could select a variety of algorithms, a variety of parameters, and then enabled users to try a sequence of reward functions along with a sequence of learning contexts. And then ultimately they submitted a preferred reward function with their learning context. That reward function was found to overfit the learning context. But in addition to that, she found that 53% of the RL experts wrote reward functions that actually fundamentally failed to encode the task in the hard case, and where there were, say 15 steps between food and water, so kind of like hard case. And so that is a very large number of RL experts that are failing to encode a relatively simple task here. And then most experts used a myopic design strategy. And they're really looking at the sort of goodness of the current step or the next state. The takeaway here is that people are really not good at reasoning over discounted accumulated reward. And this was evidenced in some of the quotes. So, one of the RL experts here, as describing how they define their reward function, they said, well, it's best not to be hungry and thirsty. So I'll set that to max 1. Being not thirsty is better than being not hungry. And worst is being hungry and thirsty. So setting that to -1. So looking at the relative goodness of different states versus reasoning about the sort of true metric of accumulated reward. This is problematic because people are experts are not accurately expressing the reward function of these domains for an agent to be able to realize high performance in a variety of contexts. But it begs the other question, because maybe it's okay as long as a person can close the loop. They were given a trial and error process, but maybe with further trial and error, maybe with further fielding of the system, they would ultimately refine that reward function. But how can you know what model a person holds of another person or an agent? So that's the fundamental challenge here. How can we assess whether a person even knows that the reward, holds a high quality model of the reward that the agent is using, to then take the downstream steps of identify deficiency and fix it up. The reason this is so challenging is that the mental model that a human holds of the reward function of a system or the behavior of any other entity, like a person, is latent. And because of that, we have a wide variety of techniques that we utilize to sort of elicit some information regarding the conception of the human's reward, preferences, demonstrations, language, specifications, critiques. All of these provide evidence of the human's held reward. And many of the techniques that are employed here, the prior literature here assumes this sort of noisy rational model, that these are observations with regard to a noisy rational model of the human's reward. But the way that these techniques are typically evaluated is by comparing against a simulated human ground truth, because we can't actually access what's in a person's head. We can't actually, determine whether the reward they think the system holds is the reward that it's actually using. So the very creative approach, recent PhD student Lindsay Sanneman sort of identified that, maybe we can develop a validated metric to assess a human's understanding of reward. And we can do that using the types of validated scales that are used in other settings, for example, in healthcare. Assessments of, say, depression. You ask a set of questions and you infer something related to that latent construct of the state of the person. And these techniques are validated using structural equation modeling and factor analysis. And so Lindsay did just that. She took a variety of sort of questions, elicitations of a person, including them providing best demonstrations, relative preferences, identifying features in their view that are important as a part of that reward function, and applied structural equation modeling to validate that a particular set of questions actually do provide information regarding reward alignment between the person and the machine. And so I point you to this because this is actually the first validated metric we have for assessing reward understanding in human autonomy teaming. And it's a survey-based approach and quite easy to apply. So what Lindsay did was actually apply it to do a head-to-head assessment of many different explainability techniques. To what extent do these variety of explainability techniques actually support a person in building a high-quality model of the reward or behavior of an agent? And they largely fall into feature space and policy space explanations. And she took either the most widely cited or widely used techniques from each of these categories, and added to it some naive baselines for purpose of comparison. So for feature space, she just provided the person the reward function as it is, features and weights, versus explaining subsets of it or abstractions of it. And similarly, she provided the person with best and worst demonstrations from the policy, in addition to policy summaries and factored policies. And findings were very interesting. So she did it in the context of a few domains of various levels of complexity. And she looked at assessing reward understanding. She looked at assessing workload, subjective perception, and analyzed it using a linear mixed effects model. Now, fascinatingly, she found that never mind any of these explainability techniques, you can best support a person's understanding of reward by just giving them the reward function. This performed better than all of those families of explainability techniques, which I think emphasizes the importance of sort of rigorous study and comparison of these techniques with regard to what you're aiming to achieve. In this case, of increased transparency or increased situational awareness. But the techniques that provided full information regarding the reward function, direct approach, as well as policy and factored policy summary and factored policy approaches, actually came with a cost. They came with the highest cognitive workload. So you're giving the person full information regarding what the agent's using, and they're doing a lot of cognitive processing to be able to make use of that information to build their understanding of the reward. And then finally, she found this sweet spot. So one family of techniques, reward abstractions, yielded high reward understanding, the lowest workload, and the best subjective assessment. So this is quite exciting because it points a path forward to being able to design for these variety of human factors and be able to select the appropriate explainability technique. Thinking about supporting essay workload, and then we'll come to trust in a little bit. And so in addition to these sort of computer-controlled, computer-based studies, she did some comparable studies in real environments with kind of distractor tasks and more realistic, sort of like visually realistic environments that a person needs to attend to as they're aiming to build their understanding of a system. And again, found consistent experiment results. So we do have this very interesting trade-off between understanding and workload as we're aiming to support our understanding of the behavior of these systems. And we have some indication that abstractions are a good technique that's balancing these different trade-offs and considerations. So now let's look at level 3. And how we can project behavior and calibrate trust in a sequential decision-making system, in a black box system. And if we can get this right, if we can build solid levels 1, 2, and out to projection 3, the potential is very good for wide and safe use of these technologies. And obviously, if we don't get this right, as we see in aviation, there are very serious negative consequences. So the goal sort of in this work, which was led by Owen Kenny, along postdoc in my lab, along with PhD student Mikal Tucker, was to sort of a challenge to look at, well, let's work with a largely uninterpretable black box approach like deep RL. And can we develop a way to kind of like do what arguably like might not be possible? Like, can we make a black box system interpretable in terms of it making transparent its decision-making process? Can we do that without losing performance? And how do we do that in a way that corresponds to supporting levels 1, 2, and 3 SA? And can we show that if we can do this, it better supports people in calibrating trust in these systems? So Owen developed a very, very creative and really cool and relatively actually simple approach for doing this, working with any black box system and working with a user that can sort of generate appropriate abstractions for your system. So he works with a user to provide human-defined prototypes, prototypical sort of policy behavior of the system. So the study he did was in the context of an autonomous car, where human-friendly or human-defined prototypes related to typical sort of images and pixel space of the car turning left, the car turning right, the car braking, the car accelerating, and then those prototypes are combined with various weights to realize a variety of behavior at execution. And so these prototypes are used as sort of a wrapper around your black box system. The end-to-end system is then retrained to achieve high performance, but ensuring that these prototypes are utilized as a part of the system's decision-making process. So the optimization process here is to collect the simulation data from your pre-trained agent. You define your prototypes and weight matrix. You train your prototype wrapper net, PW net, to mimic the original black box agent while using the human-defined prototypes. And the objective here is to mimic the original policy of your black box system and use the prototypes while doing so. So using this PWNet approach, the research question was, well, can this help calibrate appropriate trust in humans? So we have these 4 prototypes, and in the human participant experiment, the concept here is that some of the situations provided are in distribution, and some are out of distribution. And you want a person to be able to identify whether they should rely on the behavior of the system by determining whether it's in distribution to what's been seen or out of distribution. And we worked with 3 groups. So one group which received sort of the good prototypes that you can see here. One group that received like totally wrong prototypes. So accelerate shows a left turn, brake shows a straight turn, turn left actually shows a right turn, and vice versa. So this should be very confusing. Like, in other words, while the system may still be able to achieve high performance with these prototypes, these prototypes do not correspond to a human mental model of sort of concepts that would be applied in accurate in high performance of the vehicle. And then a third group was the black box group. Their explanation was, no prototypes. They were simply told the car learned to drive very well by practicing for millions upon millions of simulations. So, and this is what the sample material looked like. So the person is shown a new situation. They're asked in the prototype example to recall the car's learned concepts and then rate this car will drive safely in this situation. Strongly disagree to strongly agree. Now, very interestingly, if people are given bad prototypes, it turns out you've undermined their level 1 and level 2 essay, and they actually do undertrust within distribution situations. So you do see that effect. And conversely, people that are given no prototypes, they're just told the model is trained for millions upon millions of examples. By giving no prototypes, people overtrust in the out of distribution situations. So we do see the best calibration of trust in the case in which the model is using and presenting these human-friendly prototypes. And so, this is sort of like a proof of concept that if we aim to sort of achieve, provide the hooks and affordances to support a human's essay at level 1, level 2, level 3, we can see these benefits. As Lindsay showed, benefits in terms of cognitive workload, as Owen shows for level 3 essay, benefits in terms of trust calibration for projection of the system's behavior. So the key takeaways of this work are that it is possible to design an interpretable deep RL system that wraps around any neural agent backbone. And that these PWNets actually don't lose performance. You're not sacrificing performance, at least in the domains in which we developed and test them. The technique does show promise in terms of supporting the ability to calibrate appropriate trust in these agents. So, and I just want to note that, in the development of this work, special care, was taken to be able to incorporate sort of the human-defined, human-guided development of prototypes that would, and then to use those in a way that's sort of intricately that's incorporated, within the sort of decision-making process of the agent. It's not a post hoc explanation of prototypes that could kind of explain the behavior of the system. But it's with a black box agent, we are able to actually ensure or force that these prototypes are used as a part of the decision-making process of the system, thereby sort of avoiding the challenge we saw in sort of salience methods or feature attribution methods, in which the indicated features were not actually fundamentally used in the prediction or in the classification. So, taking a step back, as AI is increasingly deployed, in these high stakes environments, we see, a lot of interest from, healthcare, from the Air Force, other DoD settings, in being able to support SA of fighter pilots, of everywhere from doctors and nurses to, back office assistants. And I guess what I want to leave you with is, a key element of being able to support appropriate levels of human judgment is explicitly designing our models, the explainability elements of those models to support level 1, level 2, and level 3 essay. And so with that, I'll wrap up here, and I'm happy to take any questions or discussion. Thank you so much.
Thank you, Julie, for the wonderful talk. We can right now start the Q&A section, and we can take questions from in-person audience and online audiences.
That's great. I'll stop screen sharing. If I need to pull it back up a slide, I can definitely do that.
Since wait. Hi, Julie. Since I'm one of the panelists, I'll take the chance to ask you a question. So you said a lot about like in an autonomous driving scenario. What sort of, I guess how do you explain how do you project if the robot will do well in the next intersection or in the next situation? So I wonder, like in the current like autonomous driving cars, for example, the cars in some in Teslas or other brands, like how do you calibrate that trust with the autonomous car in your situations? For example, like if the Tesla sells you a new car, what do you think is the right way to say, hey, it can operate in these situations and it cannot operate in the other situations?
Yeah. So that's a great question. So Micah Ensley, who developed the essay framework, so the foundational framework, I really enjoyed. I mean, it must have been 2019 or so. It's like a 2019 or 2018 paper with an earlier Tesla model. So she developed the foundational essay framework, and also did a lot of the foundational work I mean, essay is intimately related to issues related to mode confusion. So like 737 MAX is a more contemporary set of accidents in which mode confusion regarding like the pilot's understanding of what mode the aircraft was in comes up. But there's a long history, a multi-decade long history, and sort of best practices in terms of design, how to mitigate the potential for mode confusion. And mode confusion is most prevalent when an automated system is sort of changing behavior or changing modes while a person is doing both a monitoring task of that system and some active task. And so, one question in my mind right away is, a few years ago, as Teslas were being rolled out, was, pilots are trained like for like thousands of hours to be able to mitigate these types of issues related to mode confusion, and they also have like a long time to work their problem. Like they have minutes when something goes wrong. In many minutes in a commercial aircraft. But in a car, you have like a split second. It meets all the criteria for, undermining someone's essay and raising issues of mode confusion. And so Micah Ensley actually did sort of a self-study, a naturalistic self-study of her driving one of the earlier Tesla models and documented ways in which her essay was undermined and led to instances of mode confusion. So it very, very much does exist, that this potential with autonomous or semi-autonomous vehicles on our roads. So as a part of the follow-on work, we're working with a company to like test out and field the PW nets on an actual vehicle in the context of a safety driver overseeing the behavior of that vehicle, which is a quite interesting and exciting process, because it's as you can imagine, it's not as simple as someone specifying the prototypes and then you're good. There's sort of an iterative process there. There's also sort of retraining of the end-to-end model as you learn about which prototypes are kind of necessary to be able to build a person's understanding of that system. So that's one way we're taking that work and kind of bringing it out into the real world to be able to learn more about its application. And then there's also very interesting questions about scalability. So this was a toy domain with an automated vehicle that turns out to work kind of well enough for taking it to the context of a safety driver overseeing an automated vehicle. But we're also looking at how you support a fighter pilot's essay over increasingly autonomous aircraft, and an F-16 model and its ability to maneuver is like very different than a car. And so we're trying to push the frontier of complexity of what this can handle, and sort of learn as we test with domain experts in the loop.
Can I ask my question? Hello, Julian. It was nice overview, but I take a issue with your statement on that you are very, how should I say, careful or skeptical with the healthcare, AI in healthcare. I actually think that there is the best possibility to really make a difference, because in healthcare, your measurements are finite and limited, and therefore you can make a combination of hypotheses, which is the kind of deploying an inductive process in creating multiple possible hypotheses, and then deploy deduction in decision-making when a doctor, based on all these possible combinations, have to make a decision what kind of treatment they will suggest, or more probably will work. So seems to me, recently I was approached by a colleague, Professor Harvey Rubin, who is interested in difference between knowledge and wisdom.
Mm-hmm.
About that. Wisdom, the doctor has a wisdom based on experiences, a lot of experiences, to really make the decision. So that's a deductive process. But the AI technology, or our multiple technologies, offer a broader set of possibilities, which is an inductive process, combinations, and therefore give the doctor more wisdom in his or her decision making. So that's just a thought for you.
No, that's great. I didn't mean to. I think I pulled a title from an HBR article that was sort of documenting, some of the challenge, in healthcare. My view is also that they move quick, and they're pretty far ahead compared to some of the other sectors. And at MIT, currently I'm leading a working group involving 40 companies on generative AI, where they're, as a part of the work of the future, they're sharing their use cases and their data within the company about how they're deploying their Gen AI use cases and how it's affecting work and what they're doing for training. This was one of the cross-disciplinary projects. And healthcare, the healthcare side, and they're really moving quick and far ahead, and have a fairly sophisticated approach for incorporating the technology. And it's because they've been honing this, prior to generative AI and LLMs. They've been, kind of early adopters in many other ways. And they're also sort of systems oriented, and, they're architecting this technology as a part of a socio-technical, human decision-making system. And so there's a lot to learn from what they're doing, especially what's going well for other sectors. So I didn't mean to sound skeptical at all. I'm also, equally excited. And I remember hearing one example out at Stanford where they had a predictor, and they also take implementation science seriously on the clinical side. So that's and thinking about what is the implementation science for incorporation of AI into healthcare is just a very interesting, fruitful, way to frame the problem. They had, for example, a mortality predictor. So it would give sort of a score or a number for 6-month mortality. And they were just trying to figure out how to use it. And they thought about giving that output straight to the doctor. But the doctor sort of feels like they know better, is how the story was told to me anyway. And so, really wasn't predisposed to want to rely or utilize the extra information provided by this output. So they gave it to the nurse that spends a lot more time with the patient and is also sort of an advocate for the patient and liaising with the doctor to have sort of end of life conversations. And we're able to show that by using the same predictor and sort of inserting it into the human part of the process in one area with the nurse versus the other area with the doctor, they were able to substantially increase the frequency or appropriate frequency of kind of like end of life discussions. So I think both like on the technology side, sort of the advanced technology they're aiming to bring in multiple different ways, but also in the sophistication with which they're architecting this technology as a part of human processes is very interesting, and there's a lot to learn there.
Hello, Dr. Shah. Thank you for your talk. My question is about the comprehension. So I think a big reason why humans don't really trust AI models right now is because we don't actually think that these AI models are able to comprehend the situation. And I think a big part of comprehension is understanding causal relationships between objects, people. And so my question for you is, do you think, causal inference, causal model is a essential part of creating AI agents that we're able to trust and / AI agents that are able to comprehend the world?
Yeah, I think it's a really good question. I mean, like my gut response is I think understanding of causality is also very important. Whether to some extent, like the 3-level essay model was sort of designed with sort of like a causal reasoning model, like at its core. Like if you think about, like, the presumption is that there are elements and attributes in the environment, and that is what you're bringing together to comprehend some state of the world. But your comprehension might be faulty. Like, you might sense what's happening in the environment totally accurately, but you might be making sense of it incorrectly due to poor training or due to some other reason. And then, projection, like, clearly has like a predictive and causal element to that process. But in understanding like a human's essay, like, there's no guarantee that the reasoning process a person is going through is truly, causal reasoning, right? There could be errors in it as well. And yet we function effectively in the world. But obviously we do have these inductive biases that they're employed based on, whether you get, incorporate that in a highly structured way or, through statistical inference. Yeah, I mean, I'm predisposed to sort of agree with you. Like, causal reasoning is like core and very important to this. But even if you can't guarantee a system is employing causal reasoning, I think there's ways to architect it as a part of a decision-making process with people that can have positive outcomes.
All right. Thank you very much for the talk. I have a question regarding situational awareness, which is, do people ever design systems that create some busy work for the human or offload some tasks that the AI could be doing itself just in order to keep the user engaged? Yes, that happens very frequently. So, one example is, pilots. A commercial airliner is able to fly itself, for like 98% of the process. But a pilot is in the loop for much more than that, for a variety of reasons, for skills, for to counter sort of like decrements in vigilance over time. So to ensure that they're sort of in the loop enough to be able to take over if something needs their attention. And you see it in other settings as well. So you see it, for example, with TSA agents as they're looking for threats in your luggage. There's sort of a theory, signal detection theory, that in which you can sort of modify kind of internal parameters that a person uses to detect threats in a variety of ways to achieve kind of better human machine system performance in threat detection. But one of the ways you can sort of modify an person's internal thresholds is by frequency with which you're priming them with the threats. Signal detection theory dates back to the introduction of radar and looking for threats there. But TSA agents, in part due to avoid decrements in vigilance, and in part to sort of hit that sweet spot within signal detection theory, they're actually presented with threats that don't exist in luggage. On occasion, so that they're sort of more likely to be able to catch a true threat that exists. You can imagine it's very rare, and so you need to keep them in the loop and sort of help set their threshold for looking for those threats. You can do that through training. You can do it through interaction design, for example, injecting kind of spurious threats to keep them engaged. So that's actually one of the sort of fundamental ways that you uphold situation awareness with people or with systems, is to be able to not just provide them the information they need to perform their task in that moment, but to be providing extra information such that if they do need to sort of take over or do something that's not a part of their nominal procedures, they've along the way built an appropriate awareness to be able to do that successfully.
Dr. Shah, thank you so much for the interesting presentation. And I'm interested in how we are evaluating the ground truth of how well people are understanding, say, RL algorithms, because we are trying to evaluate how well people are understanding it. But at the end, the way we evaluate how well they understand is, again, depending on the RL experts. This seems to me a bit loopy reasoning, and how we are justifying this evaluation that it is an objective estimation.
Yeah. So the assessment technique that Lindsay Sandeman developed, that's sort of akin to the assessments for sort of kind of depression scales. So that technique was validated not with RL experts, but with sort of a broader population of people. So that's important. But Serena Booth's work looking at misspecification of reward actually was done with RL experts. So you can imagine the problem is only compounded if someone is not an expert in specifying reward and also trying to build an understanding of that system's specification and behavior. But yeah, your point is right. A scale like that is typically validated for people that are not just domain experts, that might more broadly be aiming to build understanding of the behavior of a complex system.
Hi, Professor Julie Shah. I had a quick question about the real-world abstraction we were talking about human testing. So basically, I feel like that experiment had a fixed real function made from one of your students. But what if robot starts to able to create that real abstraction by itself, and then kind of articulate human to believe that they're controlling the things, but actually the robot is actually modifying that abstraction little by little bit to have that feeling that they're aware of the situation. Can we still call that as a explainable AI?
Yeah. So we're looking at variations of this because ideally, especially for more complex systems, it's hard for a person to articulate all of the sort of concepts that might be relevant to play a role in sort of a system's complex behavior. We know bad prototypes are detrimental, but there's an interesting question as to how you leverage unsupervised or semi-supervised approach with kind of some human input or human guidance to sort of realize like a best of both worlds. Maybe that, you know, we know humans underspecify. They're not explicit about absolutely everything that's, you know, relevant to their decision making. So you have to assume that, you know, on first iteration, they're not going to be giving you a full set of prototypes that that are probably necessary to represent that system's complex behavior. And then there's another interesting question, which is how that relates to issues of cognitive workload. So Lindsay's work in identifying that, you know, abstractions are really key here. In her work, it was human-designed abstractions. In Owen's, you know, work, it's human-developed prototypes or abstractions. It's a type of abstraction. But Lindsay has an interesting collaboration with another student lab, Michal Tucker, to look at interfacing this idea with emergent communication frameworks. And so you have some human guidance of abstractions that may be relevant, but then within sort of an emergent communication framework, can you refine a set of abstractions that that are guided by that, but that together can yield sort of high system performance? And they have a paper under review in which they do have an automatic framework to do that, a self-supervised framework to do that, with interesting correlations among sort of the parameters of that model to workload, as well as, you know, in their human studies, correlations to human reward understanding. So like, I think that's the ideal world, is if there's an automated technique to be able to produce and further refine abstractions that are able to hit that sweet spot between being human understandable and sort of addressing workload issues. Yeah, and so we do have some early work along those lines, but so far unpublished.
All right, we have time for one more question, so I'm going to take it, Julie. So in the last work that you talked about with the prototype specifically, would you say that wrapping around this deep RL framework with these prototypes is kind of a way of introducing a human bias into a human inductive bias into the deep RL, this black box system? And then my follow-up question is, what if these prototypes are misspecified, or what if these prototypes are wrong? What would it, probably the deep RL system would end up overfitting to those misspecified prototypes. But then would there be a way to figure that out? Like, would we need some other wrapper around it to figure out if the quality of those prototypes?
Yeah, that's a great question. So Owen's study confirms that if the prototypes don't make sense to a person, bad things happen. Like the person is not calibrating trust in the system appropriately anymore. Like you use the benefit of the prototype wrapper, but you could still achieve high performance. Like you can still emulate the original black box system, bad prototypes, because it doesn't care, right? It'll just combine them in a way to produce the behavior of the original black box system. But what he was able to show is that from the human side, you're undermining their ability to calibrate trust in that system by providing them with poor prototypes. So that points to like the importance of these being good prototypes, meaning ones that correspond to a human mental model for them to be able to use to calibrate their trust in the system.
One quick follow-up. So so you tested this on this like 2D simulated environments. How do you foresee prototypes for more complicated real world tasks? I feel like that will require a lot of effort from the human to provide these prototypes, like for an actual embodied robots with like 2 arms, manipulating objects, things like that. Like, do you see a way forward in how to do that?
Yeah, so we're actively doing that with a company, working with their engineers and safety drivers. So that's like a new process for us that we just began a few months ago, and then with some test pilots and some F-16 pilots who are kind of invested in being able to leverage these techniques for much higher dimensional systems in which the prototype is not straightforward. How you develop prototypes that are meaningful to them. For it to be meaningful to them, they have very deep expertise and we don't have it. And We're just going through that process now. But are making progress in doing so, but don't have the key insights yet about how you make this something that is scalable, especially to like the F-16 context. That's like a more open research question. But on the autonomous vehicle side, it's required only minor modifications to the approach so far, which is a positive sign at least.
All right, well, thank you very much. Let's thank you, Julie, again for her amazing talk.
Thank you so much. Thank you for having me.
Thank you so much. So some closing remarks. Please tune in next Friday, November 10th at 10:30 a.m. for our next Grasp on Robotics talk featuring Dr. Sunil Agrawal from Columbia University. And for more information on upcoming events, be sure to follow us on social media or check out our website. So thank you again and have a wonderful day.